I'm gonna check the microphone. I just want to make sure I'm not using the microphone on my phone. All right, yo, what is up? Let's see. Wanted to see if there was anything, any notes I took from last time that I need to check out. Streaming. Okay. Let's see. I think there was just, there's just this one thing. All right, so it was in this video where it's this part right here. It's this, can highlight stuff. It's this bit shifting part. I don't really see how this makes sense.
Scaled and shifted. We instead calculate log of 1 divided by square root of y. We rewrite this to log of this, but why?
Wait. Okay, I think it's right here. Negative I shifted over 1. But recall, what is I? Let's pull this up. I is what? Oh, small. Can we make this? Is this small? I love how preview is just like, nope, not going to go any smaller than this, like width-wise. Yeah, we're going to have to do this over a little bit. Yeah, let's just do it like that. Oh, you can just kind of like do it over and it'll stop. So I was, what happens with, all right. Dang, it still didn't go over far enough. So what happens with I? So what is I? I goes here. So we just take y, and we're just looking at the bits of y. We're just looking at the bits of, so y is equal to the number. So I, so I has, like, I is the IEEE encoding of this number here. And so what's weird right now the log of y. Well, let's fast forward in the video and see what kind of happens.
Here again, calculate it. Log.
Get to here.
The map thing.
So we get here, and we're like, what? I'm like, okay. There's just like two things. I'm just kind of like going back and forth between. There's just kind of like a lot of tension, I guess. So it's like, uh, um, it's like, okay. So it's just like it's. I guess the tension is like just the bits that are in Y, and then it's like the number that Y is supposed to represent. And I'm getting a little confused because it seems like he's kind of conflating the two because we were just supposed to divide Y by 2. Um, but this isn't even Y right here. This is just the mantissa of Y, and this is just the exponent of Y. This is- So this isn't actually Y. So yeah, I'm just kind of confused. Like if you had a long and yeah, you just called that like I, and you bit shifted this thing down to, that would be, yeah, that would be equivalent to saying like I divided by 2. Like that's cool because the way it's encoded is it's just the binary representation of the number. But if you have a float of I and you do like I, yeah, bit shifted over 2, that's just like, that just doesn't make sense. Like, and you don't directly do the I shifted by 2. Like you take I and you kind of like do it into, make it into like a long, and then you like do the bit shifting. So this is fine. Like if we just look at this in isolation, where it's like 1/2 of this thing, like that's fine. Kind of in isolation, we just shift this over 2, and like that's equivalent to dividing this, like these bits by 2. But but that's different from what he wrote right here. He said it's supposed to be 1/2 of the log of Y. All right, so there's actually two things that are like weird because we're supposed to be doing by half the log of Y. And back there, we're just doing I shifted over 2. That's closer to being like Y shifted over 2. But we want to shift the log of Y over by 2. So something going on here that I don't understand. I'm missing like some missing link.
And do bit shift.
Missing.
Well, because our logarithm is actually scaled and shifted. So let's calculate and understand where it comes from. Let gamma be our solution. Then we know
gamma is the solution.
That log of gamma equals to log of Y to the power minus 1/2, which equals to minus 1/2 times log of Y. Now we replace the logarithm with the bit representation. Now we replace the logarithm with the bit representation. And then we just solve for the bits of gamma. I'll spare us the details, but this is the result.
Solve for the bits of gamma. Yeah, I guess maybe where I'm getting hung up is I'm trying to translate this thing to just like this here. So this is yeah, I guess I'm just mixing up. Yeah, I guess I does contain. I mean, if the thing that we want, yeah, we're computing the log of 1 over the square root of y. So basically, like this thing is equal to the log of 1 over square root of y. Don't we have to exponentiate it now? Like, so if we calculate, yeah, the log of 1 over square root of y, like we need to do like, not, you need to like do 2 to that thing. Or that would just be like bit shifting over the result by 2. Because you're taking log base 2 of this thing.
Magic number turns out to be the remnants of the error term mu, the scaling factor, and the shifting.
So basically this thing is equal to like the log of gamma. But yeah, we still need to exponentiate it back, no?
Now we have the bits of our solution, and we can just reverse the steps from the evil bit hack to get back the actual solution from those bits. Well, actually, not the exact solution, just an approximation. This is why we need the third step.
All right, I'll let him cook on the on this last step. Thinking what I might do is I might code this up and kind of go step by step and like unpack stuff and write it out naively. So it could be that I won't like fully understand it until I actually code it up. That might be a good thing to do.
After the previous step, we have a pretty decent approximation, but we did pick up some error terms here and there. But thanks to Newton's method.
What were the error terms? Oh yeah, we did integer division, the bit shifting thing. Okay, whatever.
We can make a really good approximation out of a decent one. Newton's method is a technique that finds a root for a given function, meaning it finds an x for which f of x equals 0. For a given function, meaning it finds an x for which f of x equals 0. Root.
Okay, so finds an x such that f of x is 0. So if you have some function like this, and it's like whatever this function, and then it goes here, like it'll find this x value where f of x is equal to 0. Wouldn't want to do that. Yeah.
Given function, meaning it finds an x for which f of x equals 0. It does so by taking an approximation and returning a better approximation. And usually you repeat this process until you're close enough to the actual solution. But it turns out that here we are already close enough to the actual solution that one iteration suffices to get an error within 1%. The only things Newton's method needs is the function and its derivative. And what Newton's method does is that it takes an x value and tries to guess by how much it is off from being a root. It does so by calculating f of x and its derivative. We can write f of x as y and the derivative as dy over dx. We have the ratio between y and the x offset and y itself. So to get the x offset, we just divide y by the ratio. So then we simply...
Oh, wait, what's that? Delta y divided by dy over dx. Okay. Wait, what? Why does he do that? So delta y. So I'm kind of confused. Okay, I guess he's calling y delta y. Yeah, I got kind of confused because I would think like this should be like y here. But fine. I mean, if you just want to call that value delta y, I guess it's like the difference between like 0 and y. It's like delta y. So I mean, I would kind of think this would be more like y over the derivative at x. And I guess this is just like the value at x. So he's just doing y over. Yeah, I don't really know like another, I guess it's like y over y prime. Okay.
So then we simply subtract this offset to get our new x.
So you're trying to get the new x. So like this is x and this is like x new here. And you have y, which is equal to f of x. You have basically the slope. You have like m is equal to f prime of x. You have the slope, which is change in y over change in x. And you want to get here. So you want to get this value. So you just want to know where this thing crosses the x-axis. How do you actually get that? So he's just doing, recall, I guess, that this thing is just delta y over delta x, he said. It's equal to delta y. This is like delta y, delta x. Over delta y. This is just delta x. Okay, I'm a little. I'm just confused. He's just kind of like overloading delta y here because he's like, oh, yo, like this value is delta y, but then he's like, oh, f prime of x is equal to delta y over delta x, and like this is true that like this is what this value represents. It's just weird that he's like combining these two things together. Just kind of like confused by it. Because if you say what's the f prime of x, you're just going to get a number like 0.72 or something. So that's it. So, and that is the ratio. That's why if you increase, so like if you like increase delta x a little bit by like 1, then you know how much to increase y by to stay on the slope, I guess. So then delta y is equal to 0.72. But that's like the amount you need to stay on the slope. It's like 0.72. I don't know. If I was just looking at this by myself, like how would I do it, like without his notation or whatever? It's like, all right, you have xy here, and okay, so you have like f prime of x. I can just say it's like 0.5. So I guess like just to get the equation for the line, you have like y is equal to mx plus b. You have the slope of the line, which is just f prime of x. And you also have the pair like x, y. You call it like x1, y1. x1 plus b is equal to y1. That's not really that useful though. Like we want to find. Okay, we want to find like when we set y is equal to 0. We want to solve for x. So we have y is equal to a little confused too, because like when we calculate the derivative, we get a new function. It's not necessarily a line. I'm a bit confused. No, okay. I guess it is the tangent line at the thing because the derivative could be like a nonlinear function, but you plug in the value of x and you get a number out, and that is the slope of the tangent line. So, okay, if we set y to 0, we want to solve for x. So we say that 0 minus b equal to 5x is x. I guess we divided by f prime of x. So we get negative b over f prime of x is equal to x. So I guess we just need to solve for b. So let's do that. We have y is equal to mx. Let's go. What did we say? X new is equal to negative b over f prime of x, right? So we need to solve for b. So we have the pair x1, y1. So if you want to solve for b, let's go y1 minus f prime of x times x1. So this is equal to y1 minus f prime of x times x1 over f prime of x. So that just equals y1 over f prime of x minus f prime of x times x1 over f prime of x. And so these things cancel out. And in his terminology, not even in his terminology, in ours. So y1, recall, was just equal to f of x. And we have f prime of x here minus x1. What were we doing here? Were we doing b? Yeah, we were solving for b. We're doing y is equal to mx plus b. And then, so yeah, we say that b is equal to this thing. And right, subtracted that. And then, wait, did we solve for b somewhere? Confused. Oh, b is equal to, yeah, y1 minus, okay, but we need a whole like negative around this because it's negative b. So you have like negative, still have this negative thing out in front. So we just say it's equal to x1 minus f of x over f prime of x. And this is equal to the x new. So yeah, I guess we did get, yeah, like we got like x1, we got the minus, and then we got f of x over f prime of x. Yeah, so I guess that does check out.
The informed viewer can now verify that the last line is one such Newton iteration applied to the function f of y equals 1 divided by y squared minus x.
Why are you doing that?
Notice that y being a root of this function is equivalent to y being the inverse square root of x. I really encourage you to verify this last line of code, since it's really surprising that even though both the function and Newton's method have a division in them, the code does not, which means that our algorithm is and stays fast. Now we finally understand the fast inverse square root. It only took us the knowledge of the IEEE standard 754, a trick to outsmart the C programming language, magic bit operations, and the calculus behind Newton's method.
Oh man, there's no like dramatic send-off. Let's see this last thing here.
I really encourage you, by being a root plus 1 and is. The informed viewer can now verify that the last line is one such Newton iteration applied to the function f of y equals 1 divided by y squared minus x.
Where does this function come from? Why does he do this? It's kind of a weird function too, because he's just like, all right, there's an x in here. So x just must be like coming from outside. Like this is a function of y. There's no x here. So I guess x was, I don't even know what x was at this point.
Notice that y being a root of this function is equivalent to y being the inverse square root of x. I really encourage you to verify this last line of code, since it's really surprising that even though both the function and Newton's method since equivalent to y.
All right, first of all he's just like, wait.
We can now verify that the last line is one such Newton iteration applied to the function f of y equals 1 divided by y squared minus x.
So why are we looking at this function? Like, what's the point of this function? 1 over y squared minus x. I mean, he does say to find the root of this function, to do one iteration. Recall, the Newton iteration thing. All right, so we're trying to find when this value is 0, when this function yields 0. So it's like we guess y, and so that gives us like a y and like an f of y value. And we need to calculate f prime of y as well. I mean, we just have to do that. And then so to get a value of y that's a little bit closer, we say like y new is equal to the value that we guessed minus f of y over f prime of y. So I guess it's just like several questions. It's like, why this function? What was original y guess? And I'd say 3, like, what is x? Like, I don't know any of these things. Just confused. Where did this function come from? I guess like number 4 is like, why do we even want to find the root? I don't know that either. Like, why are we trying to find the root of this function?
Notice that y being a root of this function is equivalent to y being the inverse square root of x. I really encourage
What the?
you to verify this last line of code, since it's really surprising that even though both the function and Newton's method have a division in them, the code does not, which means that our algorithm is and stays fast. We finally understand.
Maybe this is a better way to work from it. It's like, all right, we start with this function, y is equal to 1 over square root of x. Like, this is what we're trying to compute. And how did we get to this thing?
Code, since it's really surprising that even is that y being a root of this function is equivalent to y being the inverse square root of x. I really encourage
y being a root of this function.
y being a root of this function is equivalent to y applied to the function f of y equals 1 divided. The informed viewer can now verify that the last line is one such Newton iteration applied to the function f of y equals 1 divided by y squared minus x.
So Newton's iteration is a way to find the roots of a function. So it's like, why do we want to find the root of this function? Well, the root of this function, when y is equal to 0, y squared minus x. If we found the root of this function, if we found the root of this function, if we found the value, if we found the value y such that the root of this function is 0, that value y is equal to 1 over the inverse of 1 over the square root of x, which is what we want to find. I'm not quite putting it all together.
Notice that y being a root of this function is equivalent to as dy over the y
Maybe
and the x offset
right in the beginning.
approximation. Actually, not the exact solution, just an approximation. This is why we need the third step. After the previous step, we have a pretty decent approximation, but we did pick up some error terms here and there. But thanks to Newton's method, we can make a really good approximation out of a decent one. Newton's method is a technique that...
So I think what he's kind of trying to say is that by going through like all this work, I guess like what he's trying to say is like our total problem, like the whole thing that we're doing here is we have some function, and if we find the root of this function, then that root will be equal to 1 over the square root of x. That must be what he's saying. So like if we found that, if we found the root of that function, then we would find like exactly what we're looking for. But I think what he's saying is what we really did was we found something close to the root, but not exactly. We basically found like this thing right here, which is like close, but not exactly. So we can like use our initial guess and run one step of Newton's iteration to like get even closer. That kind of begs the question. It's like, all right, instead of doing all this stuff, we could have just like ran Newton's function, Newton's iteration like many times, I guess. But I guess like instead of doing like Newton's iteration like many times, where we kind of like jump around and, I don't know, find the solution. We like in one very quick step, like got very close, and then we just do like one kind of like more step. Yeah, I gotta go to the bathroom. I'll be back. All right, so it almost seems like this last step of Newton iteration here, it just kind of like flips this whole procedure. It's almost like it kind of flips it, where it's almost like this step is like what we were doing all along. So it's almost like this video should have maybe like started with that, and it's kind of like proceeded from there. But I don't know. Yeah, it's very weird because this last step is like, all right, it's like, we thought we were doing this the whole time. Like we thought we were computing 1 over the square root of x, and we kind of proceed. But he's like, oh, at the very end, he's like, all right, what we're like really doing, or what we're also doing, or like what's equivalent to like what we've been doing all along is
root for a given formation out of a decent one. Newton's method is a technique that finds a root for a given function, meaning it finds an x for which f of x equals 0. It does so by taking an approximation and returning a better approximation, and usually you repeat the approximation applied to the function f of y by that the last line is 1. The informed viewer can now verify that the last line is one such Newton iteration applied to the function f of y equals 1 divided by y squared minus x.
So it's like what we thought we were doing Or like what we were doing is we're like, all right, we're computing the 1 over the square root of x. But you could also be like, yo, like what we were, it's like, it's like, yo, no, like we weren't doing that. Like we were just trying to find the root of this function. Like we were just trying to find a y such that this function, this f of y is equal to 1 over, you know, we were trying to find a y such that this thing is equal to 0. I'm still unclear as to. Well, I'm a little confused because I'm not sure whether this x is the same as this x, or like we started with calling this x, but like now we're calling it y. I'm not really sure what the difference between x and y is here.
Notice that y being a root of this function is equivalent to y being the inverse square root of x.
All right, maybe we can kind of like work backwards from it. So we could say y is equal to 1 over inverse square root of x. So we square both sides. We get y squared is equal to 1 over x.
A square root of x.
Let me say, so we're gonna like multiply both sides by x and then divide by y squared. So we get x is equal to 1 over y squared. And then we just subtract x from both sides and we go 1 over y squared minus x is equal to 0. All right, this is like very weird because this started off as a function of x, and then we just kind of like march along, and now, so like at this point, it's still equivalent to our original formulation. But now we're just saying like, all right, yo, this expression, we're just calling this thing a function of y over y squared minus x. Yeah. Okay. Okay. I'm digging it.
I really encourage you to verify this last line of code, since it's really surprising that even though both the function and Newton's method have a division in them, the code does not, which means that our algorithm is and stays division in pricing.
Okay. So what must be happening here? Yeah. So x is our original number. X is like, yeah, the original number that we get passed in. Okay, this is pretty cool. So here, let's just yeah, I guess fuck it. Like all right. So basically like start off here, like we're basically, our goal is to compute y. I mean, like that's basically what we're trying to compute. And so we get to this point where we get to we just like we do some algebra and rearrange terms. We get 1 over 0 is equal to 1 over y squared minus x. So we know x, but we don't know y. We want to find the y such that this is 0. And I don't know, just kind of looking at this, it's like, all right, we just have a function here. We want to find the y such that when we plug y in, this thing is giving us zeros. So because y is like the variable here, we could like test different values for y, and it's going to get like closer or further away from 0. So we can kind of say like this thing is a function of y at this point. And yeah, we're trying to find the y such that this thing evaluates to 0. And so that's what Newton's method does. So, okay. So maybe like the two formulations for this would be like, all right, we're given x and we want to compute 1 over square root of x. And then the other formulation is like, we're given x and we want to find the root of this function. So we're given x and we want to find the root of this function. We're given x and we want to compute this. I guess like a closer equivalent thing is like, all right, we're given x and we want to find the y such that y is equal to 1 over the square root of x. Let me just got a streaming idea to stream something else. I took a robotics class when I was at UT, and there was just some stuff from there, like robotics. I remember we learned about Kalman filters. There was some 3D projection thing too, which might be cool to go back and try and understand. So these are kind of like the two things here that we're trying to do. We start with x, and we're trying to find the y such that y is equal to 1 over the square root of x. Equivalently, we're saying we're starting with x, and we're trying to find the y. Yeah, again, we're trying to find a y such that this thing is 0. Such that this thing is 0. Yeah, okay. So we just took this function and we just like converted it into a form that we can use Newton iteration on. And so, like the first 2 out of 3 steps were like we found like a good approximation for y. It's like y hat thing. And so like, okay, if we actually found like the actual answer, like y star, then if we plugged in y star to this equation, it would give us 0. But we only have y hat, which is an approximation. So it's not going to be completely equal to 0. It's going to be close to 0, but not exactly. So we'll just make it like a little bit better by running one thing of Newton's iteration. Dang, okay. That's really cool. So like going back to the code, we have y. We can almost call it like y hat here. It's kind of like close, but we want to make it a little better. So we apply one thing of Newton's iteration to it.
Even though both the function and Newton's method have a division in them, the code does not, which means that our algorithm is and stays fast. Which means...
I guess we do need to calculate the derivative of I actually do need to like do this out because he didn't actually derive out like where does this 3/2 term come from and stuff. So yeah, so kind of translating this over a little bit, we have a y, and we want to yeah right, yeah, this was like our xy pair. This is our xy pair, and this is so like our y f of y pair, and the derivative at y, and we get our y new here. So let's compute the derivative. So we have y in hand, like that's our y hat value, and we can compute f of y. So like f of y hat is just equal to, yeah, 1 over y hat squared minus x. Okay, so we have y hat. We can calculate f of y hat, but we do need also to calculate f prime of y hat. So let's say what's f prime of y? So that's equal to the derivative with respect to y of, yeah, 1 over y squared minus x. And so that's just equal to the derivative with respect to y. Yeah, of 1 over y squared. And that's it. Like this x kind of like drops off here because it's taking the derivative of a constant. So this is equal to derivative with respect to y of y to the negative 2. And I'm pretty sure that this is just negative 2 times y to the negative 3. Pretty sure that's what the derivative rule is. So then we have f prime of y hat is equal to negative 2 times, yeah, y hat to the negative 3. I think that's where this, it's almost a 2/3 thing, but I'm not quite seeing it yet. So we just need to do y new is equal to y hat minus f of y. F of y is equal to 1 over y squared minus x divided by f prime of y, which is negative 2 y hat to the negative 3. All right, this is getting messy, but I guess we can just draw over here. I don't know, we could just multiply both things by negative 2 y hat to the negative 3 times y hat, whoops, minus 1 over y hat, I guess, plus x, like distributing the minus, divided by negative 2 y hat to the negative 3. I wonder where this 3/2 comes from. It's like 1.5 thing. Just doing out this algebra on the last step. Just want to make sure this thing here. Yeah, negative 2 times y to the negative 3. Yeah, that seems like what that is. So I have f prime of y is equal to negative 2 times y hat to the negative 3, which is equal to negative 2 over y hat cubed. So we have y new equal to y hat minus, I guess we can multiply both sides, top and bottom, by y squared here. So you could say y hat squared, no, minus 1 minus x times y hat squared over y hat squared divided by, let's say it's just divided by negative 2 y hat cubed is equal to y hat minus 1 minus times y hat cubed over negative 2 is equal to y hat minus. So I guess like this kind of cancels with this. It just leaves like a y hat up here. So this is just y hat minus, I guess, yeah, that just completely went away. So it's just minus 1 plus x y hat squared times, shoot. I guess let's not distribute the minus. 1 minus x y hat squared times y hat over negative 2 equals y hat minus, I guess let's distribute this through. Y hat minus x negative 2 which is equal to, we can pull out the negative 2 and minus this negative 2 thing is just plus a half y hat plus, we'll just say it's y hat over 2 minus x y hat cubed over 2. Guess we can pull out a y hat. 1 plus 1 over 2 minus x hat squared which is equal to, let's go, kind of, did I drop this term here? Should I have written y hat over negative? No, I think that already got distributed through. No, yeah, I already did that through. Okay, and then I just pulled out a y hat term here. So let's just, yeah, equals y hat. How about let's do 2 plus 1 minus x y hat squared over 2 guess that's just equal to y hat 3. Oh, there's the 3 minus x y hat squared over 2. We're getting close. Guess we could say this is equal to y hat times 3 halves minus x y hat squared over 2. Is this where the friggin', is this where the, so I mean, like, this is kind of like the 3 halves here. But you have this like x times y squared divided by 2 thing. Is that where the division's coming in? I don't know. I'm not sure. But we're getting close. So recall, I mean, and like we just have like this y times, I mean, that's like this y out front here. It seems like it. But recall, like, what were we, what's like, what is this? Okay, like this gives us the y hat prime value. It's like our new, our like y hat new, I guess, y hat prime maybe. And yeah, so we just like basically like compute this thing to get, yeah, our better estimate, our better y hat. Okay. Didn't get it exactly. There's like maybe just off by a factor of 2 in here, but this is pretty good. I'm like pretty satisfied with getting this close to understanding, like deriving, understanding this line right here. It's pretty cool. Cool.
Our algorithm is and stays fast.
Yeah, it's just
now this is a bit hack to get back the actual solution from those bits. Well, actually, not the exact solution, just an approximation. This is why we need the third step. After the previous step, we have a pretty decent approximation, but we did pick up some error terms here and there. But thanks to Newton's method, we can make a really good approximation out of a decent one. Newton's method.
I mean, yeah, you can see how good this approximation is without even using Newton. Maybe it gives you like a 10% error or something. And then you see by applying Newton, like how much the error goes down, just like one iteration. That's crazy that they commented out the second iteration because it's like potentially too slow. It's just, oh my God, it's just like such a simple looking line of code.
The technique that finds a root for a given function, meaning it finds an x for which f of x equals 0. It does so by taking an approximation and returning a better approximation, and usually you repeat this process until you're close enough to the actual solution. The informed viewer can now verify that the last line is one such Newton iteration applied to the function f of y equals 1 divided by y squared minus x. Notice that y being a root of this function is equivalent to y being the inverse square root of x. I really encourage you to verify this last line of code, since it's really surprising that even though both the function and Newton's method have a division in them, the code does not, which means that our algorithm is and stays fast.
I mean, the 3 halves, yeah, that was like 3 divided by 2. But you don't need to do that. Like you just write it as 1.5. So there technically is a division, but you're able to get away without doing that division. And then there was that divided by 2 term, but you could just do a bit shift. Yeah, I forgot the whole point of this was not the whole point, but I don't know how much he talked about like divisions being slow. Like, oh yeah, okay, he did talk about. He mentioned divisions being slow. Let me just do bit shifting instead. I know that the square root thing was slow, I guess.
Now we finally understand the fast inverse square root. It only took us the knowledge of the IEEE standard 754, a trick to outsmart the C programming language, magic bit operations, and the calculus behind Newton's method.
Wait, why does he like? why is that the? He's just everything goes away except that. That's it. That's weird. Yeah, that's so cool. Okay, yeah, I definitely want to next to kind of like live code, like go through this kind of step by step, like with the math and in like a Jupyter notebook would be really nice to have that. Yeah, once I got C++ working in a Jupyter notebook and it kind of worked. I don't think the syntax highlighting worked, but yeah, I got that working at one point. There's like this C++ Jupyter kernel. All right, can stop sharing the screen here. Zoom. Yeah, it's this Zeus thing, Zeus Kling. Like 2 years ago. I don't know. Jupyter kernel for C++. Implementation of Jupyter protocol Zeus. Wait, is this a Jupyter thing? C++ implementation of the Jupyter kernel protocol. Dang. Huh. Interpreter part of the kernel. Yeah. Oh, nice. Wait a minute. Just do this. Don't even need to build it. Whoa. Let's there. There's just get rid of all this. Wow, this is a Jupyter notebook. Yo, this is old school. Just copy and paste the code. No. QR square root. The inverse square root of, so it's 1 over the square root of 2. So this should just be a half. Yeah, nice. It's close. Just an approximation. So the square root of 8. This is, wait, the square root of 8. So for like 16, I guess. So 1 over 4 should be close to 0.25. That's crazy. Square root of 5. 1 over the square root of 5. 1 over the square root of 25. So 1 over 5 should be 0.2 around. 5 squared, 6 squared. 7 squared. 8 squared. Oh, 1 over 100. 1/10. Oh, 100. It's like 0.01 off. Okay, interesting. All right. So yeah, but I definitely okay. This is gonna be such a great environment to just like interactively play with this. I'm not gonna do it right now. Do it soon. Yeah. Okay. Yeah, that's it for this session, guys. That was great. We got through the video. I feel like yeah, this is always the thing, like getting to a point with kind of understanding the thing behind it where I kind of have like most of the picture in my mind and kind of like locked in, but it's only like 80 to 90% really understanding. It's only really when you code it up and then you like inspect the data values for yourself that it really like you can really say that you got it because you can kind of play around with it and do little experiments and stuff. So I'm excited to do that next. That seems great. So until next time, see you guys. Peace.